We're doing example 3 from 6.2. So the question is to figure out what the maximum possible volume will be for this open top box if we've got a piece of material here that is 8 by 8, and the question is how much do we have to cut out of each corner so that the volume of the resulting box would be maximized when these flaps are folded up to make the box. Okay, so I've drawn on here the piece that we're going to cut out, and the best way to approach this is to just label that side right there, the little bit that you're going to cut out, we'll call that X. And so since we're cutting out a square, of course this piece will also be X. Okay, so the thing that we're trying to maximize here is the volume, so we need to figure out what the volume of this thing is based on the drawing. So the volume of any kind of rectangular solid, length times width times height. So you have to figure out, let's just go ahead and write that, length times width times height. Okay, now the length of this thing, what is the length going to be? Well, the length and the width are actually going to be the same because they're both 8 and we're cutting out the same bit from both corners. So the length and the width are the same. We can just label them both the same way. What are they going to be? Well, once we've cut these out and folded them up, how long is that going to be? It's going to be 8 minus 2x, because we're taking 1x away here and 1x away here. So it'll be 8 minus 2x. Okay, and then the height, what's the height going to be? Well, if you think about it, when you cut this out and then you fold up this flap here, how high is that flap actually going to be? Well, it's going to be x high, because what did we do? We cut out that bit and then we're folding it up, so that height will be x. Okay, so when we want to find a volume as a function of x, we call this v of x, volume as a function of x. Length times width, and the length and the width are both the same, so this is going to be 8 minus 2x. And there's two of them, so we're squaring that, and then another x for the height. Okay, so length times width are the same, and then height. We can go ahead and expand this. So 8 minus 2x, whole thing squared, that's going to be 64 minus 16 minus 16, so that'll be minus 32x, and then plus 4x squared. Okay, and then we can distribute the x that's there, and we get v of x is equal to, and I'm going to write this in descending order of power, so it'll be 4x to the third minus 32x squared plus 64x. Okay, so there's the volume as a function of x. The thing that we're trying to do here is maximize this volume. So if you were to graph this function, it would have the shape of a cubic, normal cubic function. In fact, I'll try to just draw a little bit about what it would look like. We're only interested in what's happening in this first quadrant here. This is x, then this would be the volume here. So if you graph this function, it's in the first quadrant, it's going to look something like this. It's going to dip back down and it's going to go up again. Now, as far as we're concerned, what we're looking for is this part right here. Having an x value over here after this point right here, when the volume reaches 0, it really doesn't make any sense as far as the context of this problem is concerned anymore. So this would be like the domain of the problem here. It's just this x value starting at 0, and then whatever x value that is right there where it touches the axis. After that, it doesn't really have any physical significance to what's going on with this problem. So what we're looking for right here is this point. Okay, this is, I'll mark it as x max, and the corresponding point would be the y value here, the v value here would be v max. Okay, so notice that this is sort of using what we've been talking about, or what we've been doing in this last section, in the last chapter as well, finding a maximum value. What's true about this point right here? Its derivative is 0, so that's a critical point. So what we're trying to do next is find the critical point, and that will give us the information that we need. So to do that, I need to find the derivative, v prime of x. It's going to be 12x squared, and then minus 64 x, and then plus 64. And then remember how we find critical numbers. We set the derivative equal to 0. So we'll factor a 4 out of this, and that's going to give us 3x squared minus, let's see, 64, that's going to be 16x plus 16. Okay, and we'll set that equal to 0. And then we can just divide both sides by 4, so that 4 is actually just going to go away. So if I factor this, I'm going to get 3x minus 4, and I believe x minus 4 is going to make it work, so that gives us minus 12 minus 4, that's minus 16. The two minuses multiplied together to give us a plus. So set this equal to 0. This is going to give us two x values here. X equals 4 is one of them, and the other one is x equals 4/3. So which one of these is the appropriate answer? Well, if you think about it, the whole side here is length 8, and if x is 4, well, what is that going to mean? That means we're going to cut out pretty much half of the box right away, and that's just not possible. So in fact, that's even telling us that this value right here, that's the other critical number, that's 4. That's where it flattens out right there. So the one that we're actually looking for is 4/3. This is the one that makes sense in the context of this problem. Okay. The question asks for the, what does it ask for? What should be cut from each corner to produce a box of maximum volume. So we've answered the question now. How much needs to be cut out? 4/3 of an inch. So that's about 1.33, something like that. So about 1.33 inches should be cut out, or 4/3 of an inch to be exact. So there we go. That answers the question. Now, if you were asked also to figure out what the maximum volume is, then you could take that 4/3 and plug it back up here into the volume function. This question's not asking for that, so we don't need to worry about that here. Okay.